Number 6, the most hilarious thing about flat Earth is that the most mundane everyday observations make absolutely no sense in your model. Everyday observations make absolutely no sense in your model.
Well, that's because you're an idiot.
Because you're an idiot.
Make absolutely no sense in your...
Because you're an idiot, that's why.
Because you're an idiot. No, don't be like that. Practically everyone is.
The most hilarious thing about flat Earth is that
And I'm going to explain why you're an idiot, sir. I'm going to explain why you're an idiot so that your family will know you're an idiot, your friends will know you're an idiot, everybody here will know you're an idiot, 10 million people in the United States will know you're an idiot, and probably 100 million people throughout the world will know.
Like a sunset. A small sun above a flat Earth would simply recede high in the sky and get smaller and smaller until it fades away. It would simply recede high in the sky.
You serious?
Would simply recede high in the sky.
And that point that they converge to is called the vanishing point. This point right here is the vanishing point.
Recede high in the sky.
Now let's look at this building outside. At first glance, you wouldn't guess that all these lines point to the same spot, but they in fact do. We'll draw these lines along the side of the building and follow these lines, and you can see that all of these lines point to one spot, the vanishing point. Even up here in these towers, just check this line here, from here to the vanishing point. It follows the lines. Now let's check the sidewalk from this point to there, and sure enough, the line follows the vanishing point.
Seed high in the sky.
Another thing to remember, the sky also is affected by perspective. Let's look at this landscape. Here's the horizon line. Put some mountains in the background. Here's some trees that are obeying the rules of perspective.
Seed high in the sky.
One day you will learn, Arthur. One day you will understand.
Perspective. P-E-R-S-P-E-C-T-I-V-E. Perspective.
One day you will understand.
Perspective.
It absolutely would not retain the same angular size and set below the horizon.
It absolutely would not.
So for the information above my eye line, the descent rate is now steeper, just like with the bottles, but I have less of an angular compression rate, right? The angles are more open. So these angle pairs, the 8s or the 1s or the 11s, etc., must always remain in proportion, but diminish together according to the ceiling or floor distance. If one angle decreases, the other increases, but they are both diminishing with distance. Theta is never met along the top, again, because the horizon distance is set by the bottom. It occupies 50% of my vision, so wherever the information above my eye line is at that point, when these two halves collapse, is what I see above my eye line in my perspective. The top continues on independently, but you will never see the objects diminish in size and reach theta along the top because they will have already set into your lower horizon.
It absolutely would not retain the same angular size.
They are gone to your vision. Note also the steeper descent rate at the top. The higher the ceiling, the steeper the descent rate within our perspective. This is how our brain interprets it. The nearest ceiling or floor sets our horizon. Similarly, the nearest wall would set the vertical vanishing line if we were up against a long wall, let's say. So if we collapse our diagram here, and we press the image downward and along the top and upward along the bottom to reach a essentially horizontal line. So you see that along the bottom, the angle 8 doesn't have to travel very far to get to the purple line, but the angle 8 above has to travel quite a bit more to do that. But essentially what you're left with is basically what we see in perspective as I've depicted here in the upper right. You have the larger angles, resolution angles along the top, and a steeper descent rate characterized by the orthogonal lines. And along the bottom, you have more compressed angles and those closer transversal lines and more stabilized or shallower orthogonal lines. You also have the object larger to start out with, but then gets rapidly smaller with distance because of the how close in proximity those transversal lines are.
It absolutely would not.
And along the top, you have the object start out smaller, but it remains relatively stable because the angular size compression rate is not as great. So the angles remain somewhat large as it descends away from you. And it maintains its relative size for the most part. And at the end, it will eventually set into the horizon. So as you probably have guessed, the sun is a practical example of this. The sun and moon set because they travel a short distance in a straight line along the very high upper boundary. If we extend our ceiling to a tremendous height, you see that the rate of differential angular compression between the floor and the apparent ceiling is large, and the descent rate steepens dramatically. So the object descends to the vanishing line rather quickly while maintaining a relatively constant resolution angle as it travels. It therefore does not experience an appreciable change in size. Once it hits the lower horizon, it sets. Again, this occurs without the object having to travel very far because it is so high up. and without an appreciable change in size. Stated another way, the higher something is, the less it changes in appearance. The distance it has to travel before it sets is dictated by how far we are seeing below the eye line, which is, in most cases, about 3 miles. This is for a diffraction-limited system, but remember there are aberrations and refraction effects within the atmosphere that can alter the size of objects and distort them.
It absolutely would not.
All right, now let's see what happens when we add in our atmospheric magnification. Again, water and refraction. Water causes magnification and refraction, right? So let's bring the sun back. Oh, check this out. Refraction bends the light downward. It made the sun set on a parallel surface as it was moving parallel, the same height, the whole way over a flat surface. The refraction caused the sun to set. Not only that, well, let's bring in the beginning of that little test, and we see that it maintained pretty much the same size, too.
It absolutely would not retain the same angular size.
And of course, that's because as it's moving away, the magnification is still taking place. And so even though the sun's further away than it was in the beginning of the test, the magnification basically preserved the same size, and the refraction made it set.
It absolutely...
So he took the data from the internet and built all the layers of the atmosphere, and suddenly the magic happened, and everything started to make perfect sense. And when I say everything, I mean everything.
With 3D software, you can model the atmosphere very accurately using refraction settings. We're not talking about drawing it and making it visible, we're talking about drawing the layers with their real effects on sunlight. Once I discovered it, I told my team, guys, we've got a solution. We can test the atmosphere's effect on the light.
After we had everything fixed, we started to compare it with real life. We actually took some real sunset videos and compared them with both the flat Earth model and the globe Earth model. And guess what? If you play the 3 videos at the same time, you would not know where the flat Earth model is, because it really looks like real live videos.
Many scientists think that the flat Earth model can't work because it can't represent sunrise and sunset. What are they going to say after studying this proof? Is it going to make sense to some of them now? They can't ignore the atmosphere. And all we did to make the flat Earth model work was add the atmosphere exactly how science represents it.
It absolutely would.
So let's take a look at this video by Phuket World. The video is actually pretty brilliant. He shows not only the size of things getting smaller as they approach the horizon, but how they also seem to be affected by the angle of approach. In this example, the vehicles converge to the center point of his measurement. Despite going straight, they all seem to converge to the center at 23.5 degrees. This is a funny coincidence that his observation matched the round Earth proposed axial tilt. What he also shows is that over and over again, things dip below the camera's perspective despite being on a flat road, mostly because perspective and extremely small bumps in the road. Also, our eye's lens is curved, and so is the lens of the camera, and this is something that I don't really see discussed often. Now, we already know that wide-angle lenses causes things that are far away to curve. This is why fisheye lenses are totally ridiculous choices for filming the horizon. But at what point does the lens in our eye affect the angle of elevation, and at what point does it cause things on the horizon to converge? After all, the further away something is, the more likely it is to be affected by the curvature of our lens. You can try a pinhole camera, but the pinhole camera model does not include, for example, geometric distortions or blurring of unfocused objects caused by finite-sized apertures. It also does not take into account that most practical cameras have only discrete image coordinates. Its validity depends on the quality of the camera, and in general decreases from the center of the image to the edge of the lens, and distortion will increase. So how can we know with 100% certainty that our visual angle to the sun is not affected by any of these things? And can we know that light from the sun can reach beyond 6,000 miles away? Especially when light doesn't travel more than a few feet in the depths of the oceans. After all, when an eclipse happens, it gets dark, but we can still see the sun, so what gets illuminated and what can be seen are separate issues completely. If the vanishing point is slightly angled and the objects that approach the horizon appear lower, it's also unclear that you would be able to visually prove that the sun cannot be flush with the horizon or diverge below it due to optics. It's fair to say it never sets at 0 degrees anyway. So what does this mean? Well, if the sun turns out to be 1,000 miles high or less, then we only need to account for a 9 degree or less elevation angle at sunset. This is pretty ideal. The sun may even be less than 500 miles high. When you start to seriously study chemistry, our atmosphere, electromagnetism, refraction, and optics, an unlimited amount of doors will open for you. So the different ideas work together perfectly, and you can see how important it will be for people to continue research. And then they start to say things about the thermosphere like that it reaches 2,700 degrees, but then they make excuses as to why that won't melt the ISS. Brian Mullen had a very good video on the subject. If they claim to not be melted at that height, then how did they measure the temperature to begin with? And whatever is making the particles hotter, shouldn't that also be heating the ship? One possible explanation for the temperature increase in space is simple. They're close to the sun. We might see it go from extreme heat to extreme cold. All kinds of elements could be generated up there, maybe highly refractive elements, further layering our atmosphere. After all, if the Earth is flat, why should we assume the sun and moon are flying through a vacuum? Especially if we know that NASA is feeding everyone false information. It's much more believable that the sun and moon are something so unbelievably awesome that it would humble and amaze all of us. Also, light changes speed in water and gas. This is very important, and when you realize this, you will be amazed at how much modern religious scientism falls apart. Light can slow down anywhere from 3/4 to 1/3 of its speed through water and glass, and using a crystal you can even trap light. By use of a Bose-Einstein condensate, Danish physicist Lene Vestergaard Hau at Harvard University succeeded in slowing a beam of light to about 17 meters per second. Okay, so why does this matter? Well, there are many things you can do with light. You can refract it, changing its direction, you can diffract it, you can separate the waves, and sometimes isolate color frequencies, like Royal Raymond Rife did to analyze bacteria without harming it with the world's most powerful cellular microscope that he made. Or you can reflect it. So this can be an important problem because modern scientists base all of their measurements on c, the speed of light, which they calculate in air. But remember, air is filled with at least 30% humidity and tons of other chemicals that refract light. It's not even close to being transparent. There is so much air pressure that it can cause planes to rip apart if they fly too fast at low altitude. They never measure this speed on Earth in a vacuum chamber. Their official number for c is based on experiments done in lower atmosphere, which we can prove because people actually measure this and post those videos to YouTube. They might use an oscilloscope in a mirror, for example. Let's also consider the margin of error in their measurements and in their equipment. Now, if you are not measuring c in a vacuum, then how can you know its true speed? It clearly moves slower in air. So the speed of light must be wrong, but how much is debatable. However, if you suck the air out of a train, it will crush like a tin can. Sending lasers from Earth to be refracted back won't work either, because it still needs to travel through the atmosphere. So who can measure light in a vacuum? It's possible that it's almost infinitely faster. So why does this matter? Because it debunks the speed of light and brings relativity into serious question.
How does the appearance of a sunset never vary at all, whether it's dry or humid or raining?
Never vary at all.
And then, of course, there's this video right here, which apparently was shot in the desert, where there's going to be a lot less moisture. And so whenever there's less moisture, you're going to obviously have less refraction and magnification.
You don't get to pick the anomalies that seem to agree with your views and ignore the common observations that don't, and still call yourself an honest investigator. That is intellectually dishonest.
Never vary at all.
And that's the brand name and make of the solar telescope. Now, it doesn't have any zoom on it either. It's locked in at 500 millimeters. And we have shrinkage over here from the noon picture, and a little shrinkage over here. And as you can see, it's bigger. So as you can see on this day, the sun did actually change sizes throughout the day. And as you can see, it's starting to shrink back down again. And it isn't quite as big as the November picture, but bigger than the 4th of July. Does the sun change sizes throughout the season? Yes. Does it change sizes throughout the day? Yes, it does.
Never vary at all.
Okay, back to the Copernican principle, and this is what they tell us. The sun is 93 million miles away. Now, I'm going to show you evidence through sunsets that shows the sun light following the sun over the horizon, and it shrinks as it goes over. Now, there's no way it would do that if the sun is 93 million miles away. Okay, first I'm going to show you some footage from the ISS. Okay, now watch this animation. Watch this sunset. Now this is exactly, if they came to me and said, do an animation, this is how I would do it. If the sun were 93 million miles away. Just like that. Have the whole horizon fade evenly. But that's not what we see. Okay, wow, look at that. Look how the light lifts off the ground like a big wedge or like lifting up a sheet of paper. That's incredible footage. Okay, here's a little illustrator or a little cartoon from a website called timeanddate.com. It's really funny that they would have a perfect illustration of a sun rising and setting on a flat Earth due to perspective. Okay, these next three slides, the sun is almost set already behind the horizon, but watch as the sunlight shrinks and follows the sun. It's definitely a locally illuminating sun, not far away, not very big, and definitely not 93 million miles away.
mundane, everyday observations make absolutely no sense in your model.
Okay, remember this video from the beginning of the video? I showed you this one and how it's circling over the Earth and watch it sweep to the right like a bowler bowling it in there for a strike. Okay, now I want you to pay attention to the way the light follows the sun. The sunlight's going to shrink, right, as it follows the locally illuminating sun. Watch this. See it shrinking, following the sun? You do not get that if the sun is 93 million miles away. The entire horizon should fade evenly, just like this supposed shot taken from space of the Earth. You can clearly see the way they depict it. They depict the demarcation between day and night, or light and dark, as a long straight line. And you can see the long straight line moving as one solid piece. That means that the sunset should all fade, the entire horizon should fade evenly. But that's not what we observe, as we will see and as we've seen in the footage so far. The sunlight shrinks and follows the sun over the horizon. So these time-lapse sunsets are definitely the nail in the coffin for heliocentrism. But this particular one here, shot from above the clouds from this observatory, is the final nail in the coffin. Look at how the sun just shrinks and the light shrinks to nothing. That cannot happen, as I showed you in the when the sun illuminates the entire Earth, which it does from 93 million miles away. It has to. You don't get this isolated look at the sunlight trailing the sun. That's only possible with a small sun, close, not very high, illuminating locally. I mean, if this isn't proof to you, then you gotta take the blinders off.
The home point has been takeoff.
.444, so we have about a minute left. If you all are just joining us, this is Flat Earth sunset. As you can see, the sun is pretty much out of our line of sight right now due to perspective. As you can see, it's getting smaller and smaller as it goes further and further away, not down. And we're pretty much down to the last minute here of the sunset. And as you can see, it's just a tiny little speck, and it's gone. It's gone.
Never vary at all.
And we have shrinkage over here.
Wikipedia actually defines atmospheric refraction as the deviation of light or other electromagnetic waves from a straight line as it passes through the atmosphere due to the variation in air density as a function of altitude. So it's saying as the air gets closer to the ground, it's more dense. So atmospheric refraction near the ground produces mirages and can make distant objects appear to shimmer or ripple and appear elevated or lowered, stretched or shortened, with no mirage involved. So now, let's take a look at the sun. Is this not what we see? Can we not see ripples in the setting or rising sun? I think we are clearly seeing atmospheric refraction here. Could we also conclude then that due to this light refraction, the sun appears to be lower than it actually is, as previously stated? Now people will argue that the flat earth theory must be wrong because if the sun were circling overhead, then it must get smaller and smaller until it ultimately disappears. This is essentially what happens though. But as the sun approaches this vanishing point, the light begins to distort and refract, making it appear to sink below the horizon. In some parts of the Earth, though, this refraction does not take place. So couldn't the phenomenon of the sun turning distorted and rippled, appearing to sink and changing darker color happen on a globe too? I mean, after all, we are rotating away from the sun, which increases the distance the light is traveling to us, right? That can account for the light refraction, right? On a globe Earth then, you would need to justify that the sun is not actually moving further away from the observer, but the observer is rotating away from the sun, which we are in that model. But how far are we going? The Earth is rotating at about 1,675 kilometers an hour, 1675. Depends on where you are though, it's faster toward the equator. Now to make the math work, we would need to convert those kilometers to miles. This would be about 1,041 miles per hour. It's pretty fast. It's fast as shit. Now from 12 p.m. to 6 p.m., approximately when the sun sets, you would go 6 times 1041 miles.
or about 6,246 miles, not accounting for the curvature though. Just to make the math simple, that's about how far you would go. So that's a long way, right? Explains the light refraction, changing color, mirage? And I don't think so. Not at all, actually. You need to consider the relative distance that you are rotating away from the sun out of the whole distance. The sun is 93 million miles away from the Earth. Relatively, we are not moving far away from the sun at all in this time period from 12 to 6. In fact, we moved 6,246 miles away from the sun out of the total 93 million. So doing the math, the distance we traveled divided by the total distance is 0.006716, or 0.0672% rounded. So objects look distorted and refracted as they get further away. Good, I get that. But you're trying to tell me that an increase or decrease in distance that light travels of a measly 0.062% is going to cause the sun from looking white in a perfect sphere to dark orange, rippling, and misshapen? On the flat Earth model, these calculations are not exact, but the sun could easily go from the estimated 3,000 miles above your head at noon to 5,000 miles away from you at sunset, which is almost double the distance out of the total distance. That's almost a 50% increase, about 744 times that of 0.0672. This much larger increase or decrease in distance could much more easily explain the phenomenon of light refraction regarding the sun and the distortedness and change in color.
Why does nothing else but the sun behave that way? Show me a projectile or a plane going below the horizon as it recedes.
And that point that they converge to is called the vanishing point.
Recede high in the sky.
Another thing to remember, the sky also is affected by perspective.
Why does nothing else but the sun behave that way? Why does nothing else but the sun behave that way?
You're an idiot and a scammer.
It stays the same size because it's unbelievably far away.
Unbelievably far away.
And now I'm going to measure the angles in front of you so you can feel more comfortable. Okay? You can check his video to see if everything is correct or not. That is geometry for some people. Now, he thinks that these two lines are going to cross paths in 93 million miles, or at least somewhere close, right? Now, let's measure the angles real quick. Now let's see where these lines are going to cross path. Well, that doesn't look like 93 million miles, does it? Okay, let's measure the distance. Wow, that is just 250,000 miles.
Unbelievably far away.
250,000 miles. Come on, man.
And it sets below the horizon because the Earth is a sphere that is turning. Even a toddler can understand this. Turning.
Okay, so that's 6 hours. No movement whatsoever.
Because the Earth is a sphere that is turning.
That both it is the ether rotating at approximately 15 degrees per hour around the Earth, and that there is zero motion of the Earth around the sun.
Even a toddler can understand this.
Everybody that is measuring this with their fiber optic gyros, they're looking at that 15 degrees per hour and say, yep, there it is. That proves that the Earth is rotating. But what they're completely failing to take into consideration is all the other motions that are in play here that are considerably faster than the 1,038 mile per hour rotation. For example, the 66,000 or 67,000 mile per hour velocity around the sun around the Milky Way around the Great Attractor. In other words, all of these things are well within the sensitivity thresholds of the these ring laser gyros, and yet the only thing they measure is the 15 degrees per hour rotation. And that does change, by the way, by the latitude.
Even a toddler can understand this.
And lo and behold, as soon as we turn that Helmholtz coil on, the readings of 15 degrees per hour just went to heck. It just completely screwed with it. Well, that's a problem, you know, because if we are able to affect it magnetically / dielectrically, then that tells us that it's not the motion of the Earth that's simply causing the phase change in the light, right? It's actually the dielectric field that we are influencing.
Let me close that for you. To recap, if it is the telescope that is moving, then when it is filled with water, it has to be tipped further to see the star. If the telescope is stationary and the starlight drifting past us, then it does not have to be tipped further. The result of Airy's experiment, known as Airy's failure, was that the telescope does not have to be tipped further. This proved that it was the incoming light that was moving past a stationary telescope fixed to the stationary Earth. What is interesting in his very brief report of only 4 pages is that not once did he refer to the astonishing results that the experiment proved. This experiment was also dismissed by Wikipedia, which said, "Ether drag test," under the main article, "Luminiferous Ether." By means of a water-filled telescope, Airy, in 1871, looked for a change in stellar aberration through the refracting water due to an ether drag. Like in all other ether drift experiments, he obtained a negative result. This is a gross distortion of the truth. That he did not have to change the angle proved that it was the ether drifting past the stationary surface of the Earth.
Even a toddler can understand this.
Has there ever been an experiment done to prove that the Earth is revolving around the sun?
Yes, there was several experiments in the 1800s. Dominique Arago, Armand Fuseau, Augustin Fresnel, but one of the most famous was the Michelson-Morley experiment in 1887.
Tell us about that.
Well, they used light beams to measure whether the Earth was moving, and they found that there was no movement. The Earth has to be moving 30 kilometers per second to complete its annual revolution, and they found out that it wasn't moving. In a very precise, Michelson could have calculated it to 1/100th of what he got in his experiment. That's how sensitive his instruments were.
What did the experiment involve in terms of apparatus, so we can get a concrete understanding of
well,
what they found?
if the Earth is moving around the sun, and we shoot that light beam in the direction that the Earth is moving, okay, and then we shoot another light beam perpendicular to that, well, the one that's in the direction of the Earth's movement should be impeded in some way if it's moving through space, whereas this one that's going perpendicular would not be impeded.
Why not?
Because it's not going through space. It's just going north and south.
Okay.
Okay? And what they found, they expected to have a 30-kilometer difference between these two light beams. There was no difference. So the natural interpretation, and even Einstein admits this, Mach admits this, Born admits this, the natural interpretation is that the Earth isn't moving. So how do we get out of that? Well, you invent special relativity. And now you say, well, the reason that light beam wasn't affected when it went toward the motion of the Earth is because the apparatus shortened.
Huh?
Yeah, Michelson's apparatus shortened as it was going with the Earth in its orbit around the sun.
Wait, you're telling me that the contraction of mass was invented to explain away the results of the Michelson-Morley experiment?
Yes, and that's what my book will tell you. It's been admitted by all the scientists.
Well, isn't there any experimental confirmation that as you approach the speed of light, there's a contraction effect? The impression is that there's all kinds of experimental confirmation.
That was invented. There's no proof to it.
Really?
Yes, all the physicists will tell you there's no proof.
Not that I'm surprised, you understand.
Yeah.
I know what the scientific community is capable of in terms of mass deception.
Nobody measured a contraction, but they put it into a mathematical formula called the Lorentz transform, and it's probably the most famous equation used in physics today.
Does anyone expressly admit that, hey, we had to come up with this contraction effect because otherwise we're stuck with a motionless
Yes,
Earth?
the very guy who invented it.
Tell me what
Heinrich Lorentz.
admitted.
Heinrich Lorentz says, I don't have any other explanation to this experiment of Michelson-Morley unless I contract the apparatus. Otherwise, we're going to have to believe the Earth is standing still in space.
Unbelievable.
Yeah.
Huh?
Yeah, Michelson's apparatus shortened.
Unbelievable.
Yeah.
Huh?
Because the Earth is a sphere that is turning.
Even a toddler can understand this.
So blatantly obvious that you have to resort to your typical ad hoc antics, talking about refractive effects that defy all logic and somehow magically apply to the sun but nothing else.
When you see, for example, this situation, you must be assumed, because when you see in real time, and you can see this is from 263 kilometers, you see the sun. You know, assume we are on the ball Earth. you see the sun setting down. So in what time this situation becomes? Because when you see this, you see the sun come from up to down. So at what moment this, transition happen? When you start to see the mirage, when it start happen the mirage, when supposedly right now the sun is down, but 2 seconds early the sun was up. Because if we assume this situation, we must believe that the sun start to invert his position. Like right here. At the beginning of all this video, because there is a lot of examples of this. So right now the sun must be at this position here, and there is some videos that shows the sun come, from early going down. So at what time this transition happened? That is the first thing that I start to think, and the whole situation. The idea to looking really deep inside the standard refraction was because there is a photograph in the site called Beyond the Horizon and from the Canigou. And the nice of this picture is that this situation, which you are not looking the complete Canigou. This is what you're seeing here is the top part of the Canigou. The mountain, keep down the mirage effect. But this picture is taken from 320 kilometers away at the altitude of 300 meters. So, it's taken at 320 meters with a distance of 263 kilometers. So, if you go straight in geometrical situations, this part of the mountain never must be appear, because it's like 400 meters below the horizon, because the Canigou have 2,700 meters. And based on the calculations with the standard refraction, you will lose 400 meters of that mountain. So supposedly we must believe that this object was raised up at the horizon level and the horizon line, which is something never happens, and with a perfect silhouette definition, which is something never happened, 400 meters.
Yeah, impossible.
It's impossible. And when
without flipping upside down too, right? Because we know that in Fata Morgana, the image actually inverts, right? 180 degrees.
Exactly. And when you start,
you should see the moon actually, half the moon flipped upside down and flip flopping, and at least thinking out loud here, just thinking off the top of my head.
Talking about refractive effects that defy all logic.
Talking about refractive effects that defy all logic.
In fact, when you see the Canigou effects, it's something that is really, you can clearly see how the image of the sun begins to going down. You can see the deformation. So at this particular situation, all the indications from the atmosphere is that the image was going down, not going up, because you can clearly see how the distortion of the supposedly everyone knows that the sun is a perfect disk. So here you can see how the lights start to, deforming and pulling down.
By all logic.
Or even better, some of you talk about a dome with the sun on the other side that produces some bizarre optical effect. Apart from the sheer absurdity of this magical dome that no one has ever seen or touched, it creates big problems for you, because you also claim that the sun and moon perform other kinds of magic to push the air and water around, to get tides and storms and what have you. That would require that it is inside the dome. So which is it? Is the sun outside of the magical non-existent dome so you can pretend to get the sunset? Or is it inside the magical non-existent dome so you can pretend to get the tides? It can't be both. It can't be both. It can't be both.
You're an idiot!
It can't be both.
Sun is a personal or local objective projection. This can be verified by anyone by doing the opposite side crepuscular rays experiment, like in this animation, and see that someone looking back at someone seeing those rays cannot and will not see the same thing. A rainbow acts the same way as the sun, being that you can only see it at a specific angle, and you cannot walk around a rainbow as it will always move away from you. And you cannot see the opposite side of a rainbow. A rainbow is a source projection, and its source is the sun. Therefore, if the sun is also a source projection of an unknown source, we can start modeling the path of the sun for each observer on Earth. We did this by taking just one longitude, that being the 0 UTC meridian on Earth, and inputted the data from observations for azimuth and declination of the sun, and traced the sun object for that location for a year for each 10th latitude north and south of the equator, and just let the data run its course for a year. But the model became so heavy with data and tiny hair-thin tracer lines that even with a super machine, we couldn't render the result. After some trial and error, we finally managed to get a clear view on the end result. And even with our sun being an equal distance to the observer, the shape and layout ended up in a torus field around the Earth. But it became very clear to us that based on Ken Wheeler's research into magnetic holography, that the sun we see is projected into the electromagnetic field in the sky. The objective sun follows the magnetic field lines that are unique for each location on Earth. So the real sun is a source coming from outside of the so-called firmament, which probably uses light polarization that is projected into the magnetic field and rendered through the atmosphere. It is no coincidence that all sun arcs combined create this torus-like field, and this is version 1.0. As soon as we find out how to use equal distance 3D vectoring and a formula on the angles in the datasheets from observations, we can then get a true shape in second-by-second motion in the field lines. This torus field is by no means a stationary field, as the sun moves north and south during the year. We animated this in what we call the cosmic breath of flat Earth, and this shows that by simply increasing the current in the field from the North Pole, you then push the field south, and by lowering the current, it flows back north again. It can also be pushed back and forth by an outside magnetic field from beyond the Antarctic, 90 degrees south latitude. The southern magnetic anomaly is also a moving anomaly, and who knows what more lies beyond the southern latitudes, all of which have influence on the field. From a creation standpoint, it must have a function as well. If we animate all sun positions over a year, the animation gives the impression of a wave going around the field like an outside source pushing and pulling on the field and projecting its image, that being the sun or moon, in it. We do not know yet what, where, and how this outside source is mechanically working, so to speak, but from an engineer's perspective, everything that works like a machine or clock must have a basic principle and laws of physics to discover its nature. We just have to figure out where to go from here and what experiments can be derived to either build on this or modify the basic concept. With this concept, we can boldly say we have created a working flat Earth model that can be held up to scrutiny, evaluation, testing, and experimenting to either verify or debunk certain aspects of this model. It is therefore with great honor and humility that we present this first and only working flat Earth model with an actual base in geometry, science, and observations. In the coming weeks, we will be releasing ground views of this model to show that current sun angles are dead on correct.
Or if you bail on the dome and say it's just water, how do all those water molecules that make up around 1% of the atmosphere produce 1,000 times greater refractive effect than actual liquid water?
Or if you bail on the dome and say it's just water, how do all those water molecules that make up around 1% of the atmosphere produce 1,000 times greater refractive effect than actual liquid water?
You can see in each medium the light's angle will do something completely different. This is what is called a density gradient. Our atmosphere is a giant density gradient. It is filled with many different chemicals. The troposphere contains a lot of water. Humidity can be 30 to 70%. The lower atmosphere is mostly nitrogen and oxygen. It also includes argon, helium, hydrogen, methane, and many other chemicals. There is other levels of the atmosphere, unfortunately off limits to citizens. The highest unmanned balloon a citizen has launched into the sky was 53 kilometers. Because of buoyancy, helium and hydrogen rise. Therefore, there is a tremendous amount of those elements in the stratosphere. There is the ozone layer filled with O3, oxygen, and there is the magnetosphere. The magnetosphere can ionize the air, and obviously a magnet can have a profound effect on light. This effect is called the Faraday effect. It's where the polarization of light is rotated while it travels through transparent materials. There are many lab experiments to show electromagnetic effects on light. Also, this is a field that requires a lot more study. Some scientists say that magnets don't affect light, but consider that light is moving at extreme speeds, so a single magnet may not be too noticeable. However, a giant magnetic field such as the Earth's field can certainly affect light. As you can see, buoyancy absolutely must separate the elements of greater densities. This means that NASA is clearly not telling us the truth about the elements contained in the stratosphere, and they are probably not telling the truth about the air pressure there either. When hydrogen and helium rise, they obviously do not disappear. No, they settle at the top and they stay there. It is almost unbelievable to say that nitrogen is the most common element in the sky when there is so much helium and hydrogen rising. Not to mention other combinations thereof. Take a look at our buoyancy diagram. This is what we call a density gradient. The cutoff lines are actually pretty clear. Let's take a look at a density gradient in a laboratory. Here we can see that the light is bent downwards and then it is bent upwards. In fact, they even split the beam of light and recombine it later. Pretty amazing, right? Still not convinced? Take a look at this clip from the North Pole sun mirage. They see the sun during a time of the year where it should have been impossible. It may be due to the magnetic pole or some other refractive phenomenon. There have been many experiments to show how light can bend up or down in our atmosphere. Over the water, it would be more probable that light bends downwards very slightly near the ocean line as light descends. This is because, as you get closer to the water, the amount of water particles increase. This increase in density causes light to go from a refractive medium to an even more refractive medium. This is called Snell's law. This could add to the list of possible causes for cities to get cut off at the bottom over the waterline. What's cool about Snell's law is when you send light back angled up from the water, the light can actually bend upwards. This has been seen in different flat Earth laser tests. The experimenter has to be extremely careful to keep the laser as straight as possible, and over several miles that becomes almost impossible. Imagine shooting a pool ball into a hole 10 miles away. Snell's law is basically an equation that is used for calculating the change in angle of light as it passes from one medium to another, so we can mathematically compute and guess how much light might bend in each medium. Let's take a look at a refraction simulator online. First, you can calculate light going from air into water, like in the case of a city. Remember, the city is on land, so the water density is lower there. As you can see, the lower the altitude of light projection, the more the light falls when it hits the water. As you can see, the sharper the angle of the light, the more the light falls when it hits the water. This works in favor of a flat Earth in any case, because a city skyline would have more trouble curving over the horizon when moving from air to water because it refracts light downward slightly. However, if you are in the ocean and you shine light upwards, the reverse happens. Let's take a look at what happens when we go from water to air. Amazing, right? The broader the angle of the light source, the less it refracts. Although in our atmosphere these changes are subtle, they are significant over many miles. Let's take a look at this site here. They sort some elements by their refractive index. Notice that there are still tons of materials not on this list, and they do state that the numbers need to be verified, but this is a great reference. So we can see that hydrogen is 4 times more refractive than helium, and lucky for us, hydrogen is more buoyant. So for the 300 or more miles of atmosphere, depending on how high you guess the sun to be, light will travel significant distances bent upwards towards the observer. Extreme heat or cold from the sun can certainly forge elements, such as helium hydride or even stranger elements. It's fair to say, unless parts of space reach negative 300 degrees, we will probably not see liquid hydrogen. However, on the internet, people seem to say in some cases atmosphere is extremely cold. It creates an inversion layer, supposedly. Maybe it just depends on where the sun is. It has been estimated that there is helium hydride in the stratosphere, however. Now, if we consider that hydrogen is above helium, this element will form a nice little lens compounding the amount of refraction that the light experiences. Even a thin layer would be significant. Imagine the light passing through hundreds of tiny little lenses. In order for helium hydride to exist, it must be in an excited state, and I think the tremendous heat of the stratosphere would be a good catalyst for this. I would like to see some experiments done with refractivity of exotic materials like these. I expect it to be significant. You see, an element on its own is not even close to the refractive index of a combined element, and the direction of refractivity may indeed change depending on the combination. For example, water is significantly more refractive than hydrogen or oxygen on their own. Why the dramatic change? Because the elements form a little lens. Let's take a look at the periodic table sorted by density. Using this, we can know how some of the elements will be ordered in the atmosphere and what direction light will bend for each layer. But don't let that dominate your calculations, because what matters is the amount of miles light will travel at the angle before crossing into the next medium. Also, it matters greatly the different materials in the atmosphere. Do not limit your bias to elements only. Refraction increases dramatically when you combine elements. For example, how does ozone affect and refract light, and how thick is the layer? Don't count on government space agencies for honest statistics here. For example, when light goes from helium to lithium, lithium is only 0.23 refractivity, and helium is more than 4 times more refractive. So again, light refracts upwards, and quite significantly. Lithium passes to argon, and light will refract downwards, and it will go down again from argon to nitrogen, and then again slightly from nitrogen to oxygen. However, a big change will happen when light passes through the water in the upper atmosphere to air, which will refract light upwards again. It's hard to say how much argon or lithium is in the atmosphere, however. Ionized particles need to be considered too, and particles such as dihydrogen, dioxygen, and so forth. It's no surprise that people see sundogs and other anomalies in the sky. If you consider that dihydrogen might exist in the hydrogen layer of the atmosphere, then when moving into helium, the refraction angle will be very significant. Light will bend for potentially hundreds of miles up towards the observer. One quick note before we proceed. Explaining our world is not easy. We realize that there will be some debate over how much light is refracted, at what point light refracts up or down, whether or not there is a dome, and so forth. We are not trying to add to the list of theories. We are simply pointing out a scientific fact that absolutely 100% must be discussed. I'm going to assume that because of how many factors there are involved, that being able to calculate this mathematically is actually impossible. However, lucky for us, we have evidence that works in favor of flat Earth. It's called advanced sunrise and delayed sunset. This is where the sun sets later than it should. Sometimes the sun rises earlier than it should. This is evidence that sun's light bends upwards towards you. In fact, even according to Wikipedia, which is usually very anti-conspiracy, the sun has been seen to set and then rise again, only to set and rise within the same hour. This can be found under the entry for atmospheric refraction. Although I don't really like using Wikipedia, since news articles have been published showing the majority of Wikipedia edits in some categories come from CIA data centers. But let's use it anyways to get some ideas. First of all, their image for the sun is totally bizarre. Why do they have the sun's rays pointing upwards and then bending downwards? Don't the majority of the sun's rays come in straight? In fact, if the atmosphere bends light towards us, why does it ever get dark? Isn't the sun billions of miles in diameter? Anyways, the actual diagram should look something more like this. Here the light comes in straight and bends up, just like we calculated. First off, it says astronomers will never shoot a star 20 degrees below the horizon because of refraction. Then it says that refraction is caused by the temperature gradient, the temperature, pressure, and humidity. This is extremely interesting. Did they forget the refractive index? We just got finished looking at refractive indices, and they ignore it. But they add some useful information, temperature. This is a huge factor in refraction. You see that the atmosphere gets extremely cold in some places and extremely hot in others. You will see how much this matters in a moment. Here they say something else. They say, when the bottom of the sun touches the horizon, its true altitude is negative. Did you see that? That means it shouldn't even be there. And since they are assuming a curved Earth, imagine if they assumed a flat Earth. That would really change all of their calculations. It then talks about an example once of how the sun set only to rise again an hour later. That's right, an hour later. And then it set an hour after that. And then it rose and then set again within the next 20 minutes. This is a classic example of advanced sunrise and sunset. Then they give some formulas, although these formulas might be kind of useless because they would have to know the exact elements contained in the atmosphere and the changes in temperature, especially in the thermosphere. And then a calculation so complex would never be reduced to such a trivial equation. However, this formula is interesting. Here it says the amount of refraction increases 1% for every 3 degrees decrease in temperature and increases 1% for every 3 degrees increase in temperature. How these were arrived at is not really clear. It looks like they based this off of the previous equations and more assumptions. The numbers seem way too linear. But if this is true, then the extreme cold or heat would dramatically change refraction. Is there an experiment we can do at home to prove this equation? Probably not. And I'm sure it wouldn't really give us any help on the extreme heat of the sun and how it affects things. After all, on a hot day over the road, light starts bending all over the place. We can probably just relate this to pressure and density. Cold air is more compact with more molecules, and hot air disperses with less density. So that affects the density gradient. This is why hot air balloons rise. They say you can see certain dispersed wavelengths with a refraction corrector, which is a rotating prism, but I doubt this would work over long distances because that light could easily be blocked and reflected. Also, the refraction of light makes the calculation of stellar parallax completely impossible, especially on the ground. In fact, refraction pretty much debunks the idea that stars are traveling up to 1 billion light years to reach us. The probability that light would be refracted, curved, and generally moved all over the place, it may as well be 100%, since they're saying that there are stars that are quintillions and septillions of miles away. Even a change in a trillionth of 1 degree would cause the light to miss the Earth completely. At the very least, you would see stars disappear for a little while to reappear again. Have you ever watched a light moving in water? Notice how it bounces all over the place? It's convenient for NASA that they'll tell you that space is just infinite miles of vacuum, even though they've really never been out there. This is probably another reason they tell you the galaxy and solar system are flat, to avoid the amount of protests they would get otherwise. Also, if astronomers avoid filming stars 20 degrees above the horizon because of refraction, that alone is enough to prove to you that their calculations of parallax are not scientific or reliable. If you triangulate a 10,000 kilometer sunset at 300 miles high to the ends of the stratosphere, we get a 2 to 3 degree angle of sunset. This certainly makes the sun easier to block with air. In fact, anything within 10 degrees is worth discussing. Another reason why this subject is so important is because it can potentially explain why the moon only shows one face. Flat earthers tend to ignore this problem. The moon, no matter where you stand, shows the same side. What type of magic holography is this? Well, if you consider that the atmosphere is potentially bending light towards the observer, then it makes sense that a flat light would change its angle towards us in the atmosphere. Let's take a look at some different types of holography while we are on the subject. Here you can see a coin appear on top of a cylindrical base. No matter what perspective you view the mirror, it looks like the coin is sitting on top of the base. Try to grab it, it's not there. The trick is in the mirrors on the inside, a brilliant little design, like a cylindrical Pepper's ghost. Of course, there are almost endless ways to design a system like this. Now let's take a look at lumographic lenses. These things are completely awesome. Depending on the angle that you view the lens, you can see a different image. This type of lens is an art form. And here is CastAR augmented reality glasses. They use two projectors and reflect them off of a retroreflective surface back to your eyes. Everyone sees a unique image. Anyone can make a pyramid hologram at home. Here I filmed a holographic moon myself using a simple pyramid made from my transparent sheets. For those people who theorize that there is a dome or firmament above us, whether it is made of ice or any other material, that could definitely reflect light back to the observer at various angles. In addition to reflected light, there is projected light. Light from a projector expands as it moves away from you. However, this also depends on the shape of the lens. A flat light source like a television screen would cause almost no increase in size as you move away from it. Perhaps this is why the moon and sun have a slightly round appearance. It would also be another possibility to explain why the sun does not shrink as much as people anticipate. Also, the further you are from the sun or moon, the sharper the angle is to them and the greater the refraction. Also, the more miles the light must travel through the thermosphere to reach you, and the more profound a small change in angle will be. Have you ever seen a moon set? Have you noticed that it almost always seems to move faster in the sky the last few moments as it descends? The sun seems to do the same thing. Right before sunset, it quickly drops a few degrees. Why? Finally, on this subject, we can see hundreds of examples of sundogs, double suns, double moons, and other things like this in the sky. It's hard to make sense of these sightings and decide which ones are valid. However, multiple suns is a pretty common occurrence. Also interesting is the alleged sighting of Rahu, which is a semi-translucent disk said to be the cause of eclipses. Something similar to this could cause the moon's phases. Or, considering that the sun and moon are constantly refracted, this introduces a wide new range of possibilities for the moon's phases.
Do something to explain a sunset. Mundane everyday observations make absolutely no sense in your model.
This is a follow-up to my last video about Bob the Science Guy, where he looks at a photo of this, the shadow coming off Mount Rainier, and proclaims that we live on a spinning ball because of this photo. And so what this video is about is I'm going to show that this is actually proof that we live on a flat Earth. Well, let's go.
Now, most people that would look at this photograph would realize that in order for the mountain to cast that shadow on the clouds above it, the sun had to be coming from an angle or an altitude lower than the peak of the mountain. This is not something that really needs to be explained most of the time. It's rather self-evident.
Well, actually, it's not self-evident, Bob. Not if you rigorously investigate possibilities of why or how this could be happening. And you know what's going on? The top of the mountain is actually above the clouds. So, and what we see there is a shadow cast from the top of the mountain. You see, it's impossible to cast a shadow on the underside of clouds when the object that's casting the shadow, the top of the mountain, is above those clouds. The only possibility is casting a shadow down on the clouds, and that's what I'm going to show you in this video. I'm going to prove to you that the sun is always higher than the peak of the mountains. And I'm going to show you that this shadow that you think is going up is not going up. It can't be going up. It's impossible for it to physically actually be angled up. It's only visually angling up. Okay, let's go. So I have these new photos, Bob, taken by mountain climbers on the top of the mountains at daybreak, okay? And so I'm going to use what you just said, looking at this picture. Ready? Now, most people that would look at this photo would realize that in order for that mountain to cast that shadow downward onto the tops of the clouds at daybreak, the sun had to be coming from an angle or altitude higher than the peak of the mountain. This is not something that needs to be explained most of the times. Bob's arrogance right there and condescension. It's rather self-evident. Well, Bob, you're going to eat those words, right? Because you just debunked the spinning ball. Because all the shadows are down on top of the clouds, which means the sun has to be higher than the peak of the mountain in order to cast a shadow on the top of the clouds. Woo-hoo-hoo-hoo. Yes, my friends, Bobby. And this is daybreak. Excellent work, Bob. You just helped debunk the spinning ball Earth. All right, back to this picture for a second, Bob. Besides all the logical fallacies and presuppositions you just committed in your opening statement, there's another one that you did in there, and I covered these in my last video on you. And so here you are, Bob, jumping to an absolutely amateurish and wrong conclusion because you don't understand perspective. You're making an amateurish declaration, especially for a self-proclaimed science guy who should know enough to investigate more rigorously a visual phenomenon such as this, and not assume this or that or the other. You're assuming that the shadow is going upward. And you're assuming that for two reasons, Bob. One is because you believe the Earth is a spinning ball and that sunset and sunrise is caused by the rotation of the Earth and having the sun being physically lower than the mountain. The other is that you don't understand perspective, even though you claim to. Now, I know you guys make fun of it and call it flirspective, and the only reason you call it that is because you don't understand it. You've never learned it. You understand, right, that those clouds are not actually angled up and that the shadow needs to be cast on something. So the shadow is cast on the clouds. And so the clouds are parallel to the ground. They are not actually angled up. So what you're seeing is a perspective illusion. Okay, here's an example. I made this. This is CGI. I know you guys don't like CGI. You made a big deal out of that CGI image from my last video and said that, oh, why don't you represent it with a photo? Because you can. It won't look like that. Well, I got news for you. I'm going to go out and get that photo for you. It'll be in my next video, so stay tuned for that one. Anyway, so this is an orthographic view of a shadow, or side view. It's 2 miles high off the ground, 2 miles off the ground, and it's a mile wide, and it's cast on the clouds. And looking through this little window, this is what it would look like, right? Clouds are parallel to the ground. This shadow would go right across the screen like this, right across your vision, and would be parallel to the ground. Now, if you look at it head on, and it's coming towards you, okay, that's going to be on your eye line, right? And that's going to be your perspective view. It's going to look a lot different. Now, brace yourselves, because this is going to wreck your little claim that this shadow is going up. You are completely missing the boat, because you make fun of perspective and you don't understand perspective. You're going to be proven wrong right now, okay? Hold on to your seat. Here we go. 3, 2, 1, boom, bam, there it is. This is the same shadow as the orthographic view right here, but this is head on. And it's the same as this, Bob, your picture of Mount Rainier's shadow. Here's 2 miles off the ground. Here's 2 miles off the ground. Here's 2 miles off the ground, or 2 miles high. Here's a mile wide, what it looks like way back there at the horizon. Here's what a mile wide looks like here. Here's what a mile wide looks like here. It's climbing in the sky visually, but in reality, it's dead straight, flat, horizontal, parallel to the ground. Boom, boom, boom. And this proves that CGI that I did in the last video. This is how it appears to go up. Okay? Sorry to destroy your ball Earth evidence. It's not. It's flat Earth evidence. And notice that the shadow starts right below the peak of the mountain and at the top of the clouds. And that shows you that the peak of the mountain is up in the clouds. So the shadow is starting below the peak of the mountain. And it's staying parallel to the ground. It's not actually coming up, and it's not actually spreading out. It's just flirspective, Bob. Okay, big mistake you guys make in your arrogance, right, and your quickness to make fun. You idiots miss the obvious. And what's obvious here is that the shadow cannot be going upwards because the shadow is on the clouds, and the clouds are not going upwards. The clouds are parallel to the ground. Okay, so I don't want to get too involved in this right now because I will cover this in my next video. I'll cover all the perspective of the shadows like that you see in and around and on these mountains. Okay, so this is a picture from the top of Mount Hood, and it's over 11,000 feet high. And at the crack of dawn, it's casting a shadow on top of the clouds. Okay, so what would that look like underneath? Well, let's go to the picture you put up. Or even better, let's see this picture that's more head-on so you can see the exact relationship. On the ground, from where you're standing, the person who took this picture, this is what you would see. So the sun is not casting its shadow upward to the underside of the clouds. It's casting a shadow on top of the clouds, which is also shading the bottom of the clouds. But now I know somebody's going to say, yeah, but look at the underside of the clouds are lit. That's another one you guys do. Well, it's reflection. It's primarily reflection, you know, because of the fact that you can see when you're standing by water like this, that reflection between you and the sun is only for you. Someone on the side cannot see that. See how the clouds get lit up just between you and the sun? That's unique to the observer, right? Two people standing on the beach both have a line between them and the sun, right? But it's not real. It's just a reflection. Okay, and the reflection, you know, is different than the shadow. The shadow is something that is actually there and everybody can see it from different angles. A reflection, if you look in the mirror, you may see yourself. If you change your angle, you won't see yourself. You'll see something else. And somebody else at a different angle looking in the mirror will see something else entirely different. So being that the sun is lower than the clouds from your perspective, that's why it'll appear to light the underside. And that's it. Okay, so if you guys want to see any more on this, I did a video about how the underside of the clouds are lit. I'll leave a link in the description. Okay, check that out. And so there you go. This is awesome proof now for the flat Earth, where the sun always stays above the height of the mountains and casts the shadow down, unlike the spinning ball model where the sun would actually go below the clouds and the peak of the mountain. Because this shadow cast, this supposed shadow being cast on the underside of the clouds is not what's happening at all. It's the shadow cast from above the clouds that's darkening the entire cloud. And this is what it looks like from down below. And this is what it looks like from above. So you looking at this picture, you might actually think that the shadow is going up. Well, if you think that, you probably think that the clouds are actually getting higher as they get near you. Or that these light poles are actually getting taller as they approach you. But they're not. They're parallel to the ground. Okay, so a real quick way to get these two photos, because how are they the same? I mean, this one's spreading out weird like that from the ground level, and on top it pinches off. Easy way to get this is just look at some train tracks. right? The tracks opening up as they come towards you is the view from underneath the cloud, and the way the railroad tracks pinch in the distance is the view from above the clouds. Okay, so let's go higher. Let's go up to Mount Rainier. And a shout out to a couple of commenters who mentioned that the top of Mount Rainier is actually above the cloud layer. So I did some digging and research, and sure enough, yep, it is. So here's a picture from Mount Rainier, and at daybreak, again, you can see the shadow goes down, and it forms a pyramid, a nice perspective pyramid, on the top of the clouds, which is only possible if the sun is above the peak of the mountain, right, Bob? And again, this is daybreak. Okay, and here's another one from the top of Mount Rainier. No clouds present that I can tell. The shadow is being cast on the ground. Daybreak again, proving, Bob, that the sun has to be higher than the peak of the mountain, and Mount Rainier is over 14,000 feet. And one more thing to point out here is that the top of the mountain, that's just above the cloud layer, is right where the shadow starts on the mountain. Could this be more evidence, Bob, that the shadow is actually on the top of the clouds? Just like we see here, because the top of the mountain is above the clouds, and that's where it would cast its shadow? And isn't that evidence for the flat Earth, where the sun is always above the mountain, as opposed to your model where the sun goes down due to the rotation of the Earth and is actually below the mountain? I love that this is something you brought up as a spinning ball model proof, and here I've just turned it around and showed it's really a flat Earth proof. Thank you, Bob. And Bob, I realize your spinning spaceball religion is being destroyed right now. You're triggered, but get a grip, man. Put the hammer down. Bob, you're backing a loser. The ball Earth is over. It's time to get on the P-Brain train, Bob, and head to Truth Land. Okay? Come on. Let's go on. So let's go up even higher. Okay, and here we have Mount Denali, also known as Mount McKinley. Mount Denali. Shadow down on the ground. Again, sorry, Bob, more proof that the sun is higher than the peak of the mountains. And this is daybreak. That's 20,000 feet. Mount Rainier is 14,000 feet. But let's go all the way to the Mac Daddy, Mount Everest, at 30,000 feet. And as you can read here, sunrise on Everest summit. Okay? So, the shadow is clearly down. And what does the sun have to be? Higher than the peak of the mountain? Or why don't you help me out with this one, Bob? Let me borrow a little bit from your opener again. Now, most people that would look at this photo would realize that in order for that mountain to cast that shadow downward onto the tops of the clouds at daybreak, the sun had to be coming from an angle or altitude higher than the peak of the mountain. This is not something that needs to be explained most of the times. It's rather self-evident. Yes, Bob, so this is rather self-evident. And most people would look at this and say that, yeah, the sun has to be higher than the peaks of the mountains to cast shadows downward at the break of dawn or at sunset, right? So you, like I said earlier, you just debunked the spinning ball because we always see this shadow in the morning and at the end of the day, sunset, from the perspective of the mountain, which proves the sun to be always higher than the peaks of the mountains. And the shadow knows. The shadow doesn't lie. And there you have it, folks. A thorough demolition of the supposed spinning ball proof. A delicious irony indeed, as we turn a spinning ball proof into a flat Earth proof.
Let's just say the bottom of this little stand here represents the bottom of the clouds. And so as you can see here, the light is way above, it's well above what would be the bottom of the clouds in this example. So let's see what happens. I turned off the lights and set my iPhone to record, and I'm showing myself here recording all of this with another camera, and I pulled the light back on the table, and watch what happens here. Ooh, check it out. And there's that refraction taking place again. It's got the light. It made the sun set, first of all, below the horizon in this case. And let's just show, this is just the iPhone view. I'm going to bring the cloud in here, and the platform represents the bottom of the cloud. So the sun's going down, and oop, there it is. The bottom of the clouds illuminated by a light source that's well above the clouds, moving parallel over a flat surface. So apparently it's possible for the sun to illuminate the bottom of the clouds even on the flat Earth model. I decided to repeat the test because science is all about observable, testable, repeatable observations, right? And this time, even though the previous test was done on a table with non-reflective tablecloth on it, I decided to take a piece of soundproofing that I had left over from when I was doing the audio drama for Seed the Series. And I even left the end curved up like this, so it really should prohibit any possibility of reflection bouncing off the table. But here we go again. Here's the same test, this time with soundproofing, lumpy soundproofing that would prevent any kind of reflection. And here we go. Oh, looky here. I got the exact same results. Huh.
do anything besides making idiotic videos with action movie soundtracks that contradict middle school level science.
That settles it. You are an idiot.
Wow, that is nuts.
So he's an idiot.
Yeah. Because you're an idiot, that's why.
That idiot.
There's an idiot in the landing zone.
Because you're an idiot.